Good morning everybody. We had started with the electrolytic conductance, the introductory part, the mechanism of electrolytic conduction, the difference in the conductors like electronic conductor and electrolytic conductor. In the electrolytic conduction, the different terms are used that we have seen like resistance, specific resistance, conductance, specific conductance and the equivalent conductance. Their formulas we have seen. Now let's go to the conductivity, how the conductivity is measured. To take the conductance, the conductivity cells are used and these are the types of conductivity cell. Now what is conductivity cell? First that we will see. The conductivity cell consists of a glass container in which the two electrodes are fixed and the two electrodes are the platinum electrode. This platinum electrode, they are in the form of a stout platinum foil. A foil of platinum is used and the two platinum foil, they are serving as the electrode. These stout platinum foils, these are electroplated with the platinum black, or these stout platinum foils, these are the platinum black because the foil is electroplated with 5 particles of a platinum. Hence it appears black and hence the name platinum black is in the practice. These are the platinum foils which are used. Stout platinum foil. On one side they are electroplated with the very 5 particles of the platinum. So this is how the conductivity cell is constituting of, and the solution whose conductivity is to be measured, in them this conductivity cell are dipped, they are connected to the electrical connection and then the conductivity is being measured. The conductivity is not measured directly. Here first the resistance is measured and from the resistance the different types of the conductivity, that may be the specific conductivity, equivalent conductivity are measured. These are the 3 types of the conductivity cell, those are used, and these all constitutes of a glass container in which the 2 platinum electrodes are fixed. And this platinum electrode, I have told you that those are in the form of the foils. The platinum, they are electroplated with the 5 particles of platinum to minimize the effect of polarization. Now what is the polarization, that we will see in a chapter afterwards, but these are electroplated with the platinum black. This is type 1 cell, this is type 2 cell and this is type 3 cell. The type 1 cell, this is used in the laboratories. This is the cell, type 2 cell, this is used in a industrial measurements to measure the conductivity of the different solutions in the industry. These type 2 cells are used, while this third type of a cell is used when very accurate measurements are required. So these are the 3 different types of the conductivity cell. They all are constituting of the same material, but only is the difference in their arrangement. From this conductivity cell, the resistance of the cell is measured and the resistance of solution, conducting solution is measured, and from the measurements of resistance we can calculate the conductance, specific resistance and the equivalent conductance. These all quantities can be measured if the resistance of the solution is known. Ideally, to measure the resistance of the solution, the electrode which are taken, the distance between the 2 electrodes must be minimum and the electrode must have large cross-sectional area. Such conducting solutions are having less resistance. So this is the ideal condition to use the conductivity cell for the conduction. Now how the R is measured, the circuit for them, that we will see afterwards. We will first see how the calculation is done and then we will see the circuit, how the resistance is measured through the circuit. Now we have seen that the R is being measured. Now to calculate the equivalent conductance, if we want to calculate the equivalent conductances of the solution. Now to calculate equivalent conductance, as we know that that we can measure resistance by the conductivity cell. So this quantity or specific conductance, these cannot be calculated directly. We know that lambda V is equal to 1000 into Ns divided by Q. Ns is nothing but 1 upon rho, or we can say is equal to A into R divided by L. This is what is the formula. So this is the conductance. The specific resistance is equal to R into L divided by A. So this is what is the formulas that we use. Actually, wait a minute. Ls is equal to 1 upon rho, which is equal to A divided by rho is equal to obviously R into A divided by L. So this is how these conductances are. Now this rho or the specific resistance is calculated from R. For this purpose, this R must be known, and for that we know the formula for the resistance, which is equal to rho into L divided by A. R can be calculated or it can be measured from the use of conductivity cell. We want to calculate rho, but to calculate rho, this ratio has to be known. Correct? L divided by A. This value L is nothing but the distance between the electrode, and A is the cross-sectional area. So to calculate rho, to calculate this quantity, R must be known as well as this is to be known. Now, the ratio of the distance between the two electrodes and their cross-sectional area, this ratio is called as the cell constant. And if you want to calculate rho is equal to R divided by cell constant. The ratio of the distance between the two electrodes divided by area of cross section is called as the cell constant, and this cell constant is a specific constant for every type of a conductivity cell. Now to derive or to calculate cell constant, we must know the value of L and the value of A, that is the distance between the two electrodes and the area of cross section. But this cell constant cannot be calculated directly in the sense directly measuring the distance between the two electrodes or area of cross section, because the electrode is made up of a platinum foil which is plated with the platinum black. So the measurement, direct measurement of the L and A is not possible, because the electrode may break during this measurement, or the platinum black that may flake off. So this cell constant, these cannot be measured directly. So to calculate cell constant, rho is equal to R divided by cell constant, therefore cell constant is equal to R divided by rho. So cell constant can be measured by taking this ratio. Now to calculate cell constant, generally potassium chloride solution of known specific resistance is known. The KCl solution of known specific resistance is used, and the resistance of that solution can be measured by using the conductivity cell. So once you know the R and you know rho, you can calculate the cell constant. So cell constant is calculated first, and then to calculate the cell constant, the KCl, potassium chloride solution of known concentration, a definite concentration and known specific resistance is used. So therefore observed resistance divided by the specific resistance will give you the cell constant. And once the cell constant is known, we know the relation between Ls and rho, right, is 1 upon rho. So this is equal to Now in the form of a cell constant I am going to write the formula. The R rho is nothing but R upon cell constant. So Ls is cell constant divided by R. So specific conductance can be calculated if you know the value of cell constant and just the observed resistance. And then you can calculate lambda V by 1000 into Ls divided by C. If you know the concentration of solution, if you know the specific conductance, then you can calculate lambda V. So this is how the value of equivalent conductance can be calculated. Now the conductivity water, what this concept is? Conductivity water. Actually, the solution whose conductance is to be measured, or the substance whose conductance is to be measured, its solution is made in the conductivity water. Now therefore, what is the conductivity water? The conductivity water is prepared by distilling first the distilled water again. That means the distilled water is distilled again, and in that distilled water a very small amount of the solution of potassium permanganate is added in a hard glass tube, and the solution is distilled. Now the water constitutes of carbonic acid, that is H2CO3, which dissociates as very quickly as H plus and HCO3 minus. And due to this present ions, water shows a very little conductivity, a specific conductivity of 0.8 into 10 to the power minus 6 per ohm per centimeter. So this is the conductivity water. Now let's see different problems, and in those problems we will see the calculation of equivalent conductance from the observed resistance. The first problem, the problem is 0.5 normal solution of a salt occupying a volume between two platinum electrode 1.72 cm apart of area 4.5 cm square has a resistance of 25 ohms. Therefore, calculate equivalent conductivity of a solution. See therefore what we have given in the problem. 0.5 normal solution, that means concentration of the solution is given, and that is 0.5 normal. A salt occupying a volume between two platinum electrode 1.72 cm apart. That means the distance between the two electrode 1.72 cm that we have given, of area 4.5 cm square, has a resistance of 25 ohms. So calculate equivalent conductance. So this is the given data, and we have asked to calculate lambda V. We know the formula for lambda V, which is 1000 into Ls divided by V, where Ls is specific conductance. Sorry, this is C. To calculate lambda V, we must first know Ls. We must first know the Ls. Ls is equal to nothing but cell constant divided by R. So to calculate specific conductance, we must know cell constant and the observed resistance. Now, the observed resistance we have given. We have to calculate cell constant. So cell constant is nothing but L divided by A. Substitute the values. 1.72 divided by 4.5. So cell constant is 0.3822 centimeter inverse. This is the cell constant. Now you can calculate Ls. So Ls is equal to 0.3822 divided by observed resistance, that is 25. So your specific conductance is 0.0153 per ohm per centimeter. Now you know Ls, now you can calculate lambda V. Lambda V is equal to 1000 into Ls, 0.0153 divided by concentration. We have given the concentration of solution 0.5, and this is nothing but 30.58 per ohm centimeter square. So this is how the equivalent conductance is calculated. From the conductivity cell, you cannot directly calculate lambda V or specific conductance or specific resistance. We can calculate only the observed resistance. So from the values of observed resistance and cell constant, we can calculate the other conductances, that is specific conductance or the equivalent conductance. One more problem we will see. The problem is the resistance of N by 50 solution of KCl. We have given the resistance of N by 50 solution of KCl at 25 degrees Celsius is 400 ohm. So this is what is the resistance of this KCl solution is given. If the specific conductance of the same solution, that means Ls for the KCl is given, and it is 0.002765 per ohm per centimeter, and R of the resistance of the 0.01 normal solution of acetic acid at 25 degrees Celsius is, now this data is for KCl, now this is for 0.01 normal acetic acid solution. For this you have given the resistance, and that is 815 ohms. Calculate the equivalent conductance. See, two different solutions, their resistances and different data we have given. This is the data for KCl is given. This is the data for acetic acid, and the equivalent conductance of 0.01 normal acetic acid we have asked to calculate. Then for what purpose this data is given? Actually, we know that to calculate lambda V or the equivalent conductance, we must know specific conductance. To calculate specific conductance, we need the value of observed resistance that we have given. But we also need the cell constant. The cell constant is not given here. So from this data, we can calculate the cell constant. Now directly L, value of the distance between the two electrode and area of cross section is not given. We have given the value of R and Ls. Now cell constant, we know that is equal to La, which is equal to R divided by rho. Right? So this is nothing but R. 1 upon rho, 1 upon specific resistance is nothing but R into Ls. So cell constant, these two values we have given here. So 400 into 0.002765. So cell constant is 1.106 centimeter inverse. This is what is the cell constant. Now we know cell constant as this solution is taken in the same cell where this solution is taken. For this measuring the conductivity of this solution, same conductivity cell is used. That means the cell constant is same here as well as here. Therefore, we are now going to calculate lambda V for the acetic acid solution. Here, the concentration of acetic acid solution given is 0.01 normal. Now, we'll first calculate the specific conductance. We know R, we know cell constant, and the relation of specific conductance, cell constant and the R is Ls is equal to cell constant divided by R. So cell constant is 1.106 divided by R. How much is R? 815. So Ls is equal to 1.3571 into 10 to the power minus 3 per ohm per centimeter. So we know specific conductance now. Now we can calculate lambda V or the equivalent conductance for 0.01 normal acetic acid as 1000 into Ls divided by C. Substitute the values. 1000 into specific conductance 1.3571 into 10 to the power minus 3 per ohm per centimeter divided by the concentration 0.01, and this is 135.71 per ohm centimeter square. So this is how we have given the data related to two solutions, but this data specifically is given to calculate cell constant, and same conductivity cell is used to measure the resistance of 0.01 normal acetic acid. So cell constant has not changed, only the conductivity will change, and the equivalent conductivity we have calculated. Rest of the problems we will see in the next lecture.